Okay, so the exam was supposed to be on 12th. Our exam is on 12th. 19? November for the first midterm. He says that it overlaps with another exam. Well, let's discuss it when all 6 or 7 of you are here. Okay, I mean, I just fixed the date so that we can change it if necessary. I don't really have a fixed date. When all the students are here, we can arrange another date. Yes, now, questions. I am assuming that I can convince you to ask questions more easily this time. I'm hoping you will be volunteering.
I try to understand the symmetry of the green function. But there is no physical interpretation for explaining its symmetry. It's mathematical, some integral equations, and it shows it.
Well, that's also, I mean, there is a proof in the book. It's just a couple of lines that it has to be symmetric. Basically, it's based on the Green's theorem. And if you go over the proof, if you remember, the Green theorem basically states that if you have a function, if you have two functions, phi and psi minus psi, you change their order, phi. This is equal to the surface integral of phi times the normal derivative of psi minus the other way around. This is what Green's theorem is about. And if you take phi to be, let's say, to prove that g of r prime is equal to g of r prime r, what the book does is it just takes phi to be g of, let's say, let me give it different names, some x and r and x, and psi to be g y and r. These are all vectors. And then it also assumes the Dirichlet boundary conditions so that phi is equal to psi is equal to 0 on the boundary. Sorry, this is, I think it was r, y. Right? So it satisfies the Laplace's equation with the Poisson equation with the Dirac delta source, or the Laplacian acting on G was equal to Dirac delta with certain coefficients, R and X. No, not R and R minus X, let's say, if R and X are the arguments. So if you just take, this will be, if you take psi to be the Green's function at the points R and Y, it just becomes Dirac delta, three-dimensional R minus Y, and this becomes the Dirac delta of R minus X. So psi was G R Y, and phi was G R X. You just take the integral, the first one becomes Gyx, the second one becomes Gxy. This is 0. The second term is 0 anyway, because on the boundary, phi and psi, they are both 0. So g of xy minus g of yx, which is the left-hand side, so it just becomes 0. So you prove the symmetry for the Dirichlet boundary conditions. And of course, there is a problem of why should they be zero? Are there any physical interpretation that we can give to this, the Green's function to be zero? Well, I have such a physical, let's say, explanation. What's the Green's function physically? Okay, it's a solution of the Laplace equation with a Dirac delta source, but what does it correspond to physically? In terms of electrostatic potentials, etc. Let's say we have a conductor, grounded conductor, so that we have the Dirichlet boundary condition. Then what is the Green's function? Can we interpret the Green's function as the potential of some kind of a charge distribution? Which charge distribution? What kind of a potential? Unit charge. Where? Unit point charge, not necessarily at the center. So let's say this is your point Y. You put Q is equal to 1. Then at the X prime, the potential is nothing but the Green's function evaluated at X prime due to a source at the point Y. Well, let's ignore the X prime. This is what Green's function is, right? Let me imagine I put two charges. I put another charge, let's say, at the point X, Q prime. If I put not unit charge Q, the potential will be Q times the Green's function. Now, what is the potential energy of this system? It's just Q prime multiplied by phi at the position X, right? The potential at that point is phi of X prime. I bring another charge over there, Q prime. Of course, when I'm bringing this Q prime charge, I'm assuming that nothing is really changing. So this is the potential energy. Now let me look at similar problem. I take the same charge distribution, same system. Can't I say that the charge, the potential energy of the system is also equal to Q? No, sorry, this is Q prime, Q, G, X. Isn't it the same thing as Q times phi, let's say prime, due to the charge Q prime located at the point Y? But this would be equal to, I have a charge Q prime multiplied by the Green's function, which is the potential created by a single point at the point Y due to a charge at X. So this kind of indirectly, let's say, just saying that these should be equal, G of X, Y should be equal to G of Y, X. Well, there's a slight point that I'm not so sure, by the way. Now, when I'm writing this term, I said that, okay, we bring the charge Q prime at that point and at the same time assume that all the other charges are fixed. In that case, U is equal to Q prime times phi of x. Is that really true? Do I need to have all the charges fixed at their positions? Because on the other case, if that is true, I would be saying that when I'm bringing this charge Q to its final position Y, I should be keeping all the other charges fixed. But the other charges are created by the Q prime at the position X, and hence they will be different in both cases. The charges on the surface of the conductor will be different. Is that a problem? So is there such an ambiguity, such a problem here? Is this a problem? The charge distribution will be different, fine. But is this a problem?
We also create potential.
Hmm?
They will also create potential at the one point.
Sure, sure. So if the charge distribution in both of these problems are different, for example, I mean, in this example, what I assume that first I bring the charge Q. I put it over there at the position Y. It creates a potential distribution. I freeze the charge distribution. I freeze the charge distribution, bring this charge Q prime at the position X, and calculate how much work I had done. So this is what I call the potential energy of the system. This U over here corresponds to that. In this configuration, what I did was I brought the charge Q prime at its position. Then there's some charge distribution, which will be different than the previous charge distribution. Then I freeze the charge distribution and bring the Q charge to the final position Y, and calculate the potential energy of the system. It will be given by this expression over here. But now the final result, the potentials will be different because both cases have different charge distributions, right? So how can I equate the two? If I cannot equate the two, I cannot talk about the symmetry. So the two systems will have different charge distributions where? On the boundary. So due to this different charge distribution, there might be some change in the potential energy of the system, right? What will be the change in the potential energy be proportional to? No, not the differential change, but the total change in the potential energy. It will be some kind of charge multiplied by the potential. What is the potential of the charges? Potential on the point where these charges have changed? 0. So, yes, in both cases, in this case and in this case, in these two different ways of creating the final state, calculating the potential energy need not be the same because the charge distributions that we are talking about on the boundary are different. But all those charges are at 0 potential and they stay at 0 potential. So if you move one charge from a 0 equipotential to some other point on the 0 equipotential, there is no work. The internal potential energy does not change. So although these systems correspond to different final total charge distributions, they still have the same potential energy. They should have the same potential energy. And hence the Green's function has to be symmetric. And now we also know where the Dirichlet condition comes into the game. The potential at the boundary should be 0. Or the potential has to be constant, let's say. If the potential is constant, if the boundary is an equipotential surface, Then just moving charges in the equipotential surface does not change the potential energy of the system. So this is the reason why the Green's function should be symmetric. Convinced? So you are also showing up on Friday? Okay. Okay. Good enough. Other questions? No volunteers? Total integral is always 4 pi.
But in the book, it says 2 pi.
The solid integral of solid angle over where? The infinite plane. You see, this is you have an infinite plane, right, of dipole layer D. Yep. So you are integrating this D over all the solid angle. What is the value of D in this direction? I mean, this is the infinite plane. Let's just assume it's straight, almost straight. What is the in this direction? What's the dipole density? Is there a dipole layer in that direction? Yeah, you see, the layer is this one. This is my layer. It goes to infinity in that direction, in that direction, in that direction, in that direction, okay? Let's just assume it's flat, plane. The dipole layer in that direction, is there a dipole layer? No, so D is equal to 0 in that direction. So the book is not integrating over all of the solid angle. It's only integrating over this solid angle. Half of the sphere, in a sense. So it gives 2 pi D. Instead of the 4 pi, it's just 2 pi D because the plane is only in, you can see the plane only if you look at half of the directions, not the other half.
Isn't the localized on the surface?
Yes. These, you see, when the book writes this expression over here, or phi is equal to D over the solid angle. When the book writes it in this form, what he's saying, D is localized on the surface, but what it's saying is, if you are, for example, calculating the potential over here, divide all your angles into solid angles, all your directions into solid angles. So there will be a contribution to the potential at this point, R, due to this solid angle, d omega, and the contribution from this solid angle is d multiplied at this point r, let's say r prime, d times r prime multiplied by this solid angle. And that is the contribution to the potential at this point from this angle, from this area. So it is localized, but when in this integral, d just means the dipole density on the surface. D is always on the surface in a given direction. So if there is a surface in that direction, then you should use the dipole density of the very small patch, surface patch in that direction.
Minus sigma, because of the sigma charge distribution.
if D is, yeah, it says that D is the dipole density. You can create a,
Small.
which small D?
Yeah.
It goes to 0. 0 is a constant. Yeah, it works. Whenever I pick up, there comes a question. Yes. Ask them, not me. I'm answering already too much. You just go to a bit to the side so that you don't turn your back to your friends. Turn around to your friends.
For example, the point 1 meter apart from that charge, the divergence would not be 0. Right?
Divergence of what?
Electric
Is that the question? So here you have your charge Q.
field. Part of the question.
Okay. So you have a charge Q at some distance. Is the divergence of the electric field 0 or not?
Not 0.
Is it or not? Non-zero. Okay, let's take votes. Non-zero and 0. So we have one non-zero. 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 So what is it equal to? 4 pi cube. So it's constant. What do you think? Are you convinced?
There's a formula that says as well, divergence of E is 4 pi sigma r.
Sigma or rho?
Sorry. According to this, should be 0. We have no density apart from the charge.
Do you agree? So that's what his claim is. Divergence E is 0 at that point because the charge density is non-zero at that point. So, what do you think?
Yeah, it must be up to our Gaussian surface.
Up to?
Gaussian surface that we choose.
Well, you see, in this relation, where is the Gaussian surface? So could he convince you? Or you still...
I first tried to electric field Q over R squared.
Okay.
And takes divergence. And I do not 0 point. That is final. He said 1 meter distance.
Okay. But the divergence of r hat over r squared is 0. You see, the divergence of the electric field in spherical coordinates would be 1 over r squared del over del r squared er, plus the other theta and phi components if they exist, which they don't. So this is equal to 1 over r squared del over del r squared, q over r squared. This is 0.
So if they are on the x-axis rather than using the spherical coordinates, if they both are x-axis, so
Yes. Okay, I got homework for you. To use the Cartesian coordinates to show that it is 0. What makes you think that it should be non-zero? Well, you see, this is, by the way, wrong even by just checking the units. If you check the units, divergence of E should have the unit of a charge density, that is, if you use the SI units, it should be Coulomb per meter squared. Not just charge, but charge per volume. So even the units do not match. So that is definitely false. But the question is, what makes you think that it should have been non-zero? The? So, what about the length?
That's why I thought it's not 0.
Okay, so it should be 0 at 2 meters, or? I mean,
So, it might be limited, maybe, but it's a constant.
0 is a constant, but not every constant is 0. The others? Why did you think that it was non-zero? No, give them a chance. Or why did you think it should be non-zero?
I thought it doesn't make sense. It's 0 everywhere.
It's not 0 everywhere. It's 0 everywhere except on one point. Well, you see, forget about the meaning of divergence. You know what the divergence is equal to. So the divergence is equal to the charge density. And the charge density, if you have a single charge, it will of course create an electric field, but the charge density is 0 everywhere, except in a single point. So the divergence of the electric field should be 0 everywhere, except in a single point. In fact, it's funny what this amounts to in one dimension. In one dimension, divergence of the electric field is nothing but the ordinary derivative. Nothing else. And saying that this is equal to 4 pi, we have a single charge q at the position x, let's say x0. Do you know the solution of this equation?
variance.
Hmm. Well, of course, we have to make some assumptions over here. And in general, in fact, I can just add some constant, any constant. I don't really care. Now, this is the most general solution. This is the integral of the Dirac delta. Well, not exactly the integral plus some constant. This is the constant. So of course this assumes that d by dx of sine of x minus 0 is equal to twice Dirac delta x minus x 0. Why the 2? Well, let's look at sine of x. You remember the step function, right? So sine of x, how do we define it? What's the definition of sine of x? You haven't heard of the sine function? It just gives the sign, whether positive or negative. No, forget about x over. If x is larger than 0, it's 1. And if x is less than 0, it is minus 1. Right? So this is theta of x minus theta of minus x. We had discussed the derivative of the theta function. Do you remember its derivative? 0 almost everywhere except on one point. So it's Dirac delta of x. Derivative of theta of minus x with respect to x minus delta. Well, delta minus x is the same as delta x. So if you just combine these, derivative of the sine function with respect to x is twice the Dirac delta of x. Or you can say that, okay, the derivative of the sine function is 0 almost everywhere except when x is equal to 0. And at x is equal to 0, it makes a jump of 2 from minus 1 to plus 1. So that's why we have that 2 over here. The theta function is constant everywhere, so its derivative is 0 almost everywhere except at a point, and at that point it makes a jump of 1. That's why the derivative of the sine function is just Dirac delta. Of the step function is Dirac delta, of sine is twice the Dirac delta. So basically, if you look at this expression, the electric field is uniform in one dimension. It just on one direction it is in the plus, on the other side is minus, but it's uniform. Well, in fact, this is nothing but the infinite plane. You have an infinite plane, let's say this is the x-axis, some surface charge density. Then the electric field in this example, well, it should be in the x-hat direction. And it can only, if it does, it can only depend on x. It cannot depend on y and z. So this is the one-dimensional, well, this is the three-dimensional analog which just behaves like the one-dimensional case. Okay, now let's go back. So the divergence of the electric, you see, we don't need the Gauss surface because basically these differential equations are local equations. They only depend on the properties at that point. When we talk about Gauss surfaces, we are talking about the properties of some quantity on all over the surface. The Gauss law in integral form just relates the sum of the electric field at every point on the surface. In that sense, it's a non-local form. But this differential forms, they are local. They only depend on what we have at that point. Now, the electric field in this problem is non-trivial. It's not constant. But nevertheless, at this point, let's say, there are no charge distribution. And the divergence of the electric field at that point depends only on the charge density, again, at that point. So if there are no charge densities at that point, then the divergence of the electric field at that point is zero. It need not be zero in general, but at that point it is zero. Mm-hmm.
But then, if you take a potential after the point, you always go up to 3
I didn't follow your example. I don't know about your friends. Sure. Or even if you want, you can write here.
So at some point we had some volume integral, and we had the potential at r minus r prime. Sorry. And then we had the Dirac delta of x minus, r minus r prime. And then we had in the same integral the charge distribution at r prime over r minus r prime equals to the surface integral.
Okay.
So we said that r is equal to r prime. This is. So then we got this potential outside the integral to be potential of r.
Mm-hmm.
And it is equal to the volume integral of this quantity here minus r prime
Mm-hmm.
minus the surface integral.
Mm-hmm.
So shouldn't this blow up to infinity at this point?
Ask them.
S plus part again.
Okay, show it on the screen.
Using the derivation, we had some sort of surface, and we defined r prime as the position of the charge here. And we defined r as our point of measuring the potential, somewhere here,
No, inside our volume.
inside. And we said that if r is inside the surface,
Mm-hmm.
then this integral should be equal to this at r equals r prime. But then if r equals r prime, this thing blows up to infinity. I mean, this is the same volume integral.
degrees of the book solved this issue. And
Ask them, not me. First, they should try. Did you understand the question? If not, you should ask him to clarify his question.
I missed the derivation of what?
you use the second theory.
Well, if you have a surface that is not in general 1 over r minus r prime. So basically, if we are setting r is equal to r prime, then g diverges. So does this make any sense at all?
Charge goes to 0 at the same time. When you look at the dV there, rho dV is equal to the amount of charge, r minus r prime goes to 0, and also the amount of charge goes to 0. So
How much of charge goes to zero? Zero to zero, zero to zero.
if you take the limit, and then it goes to some finite code. Yeah, it goes to the potential potential by the surrounded charge. It's not that charge itself.
We're integrating over PV. We can't just PV equals to zero.
We put r prime instead of r, r.
Because they're the same.
It doesn't make sense to give infinite amount of inputs inside the function. R prime can be only one point. If you enter a parameter into a function.
didn't set r prime is equal to r. The result of integral is only gives r prime is equal to r as some number. But the rest is the zero. This is the evaluation of integral that also our volume contains r equals r prime. But we are proud of the single point. The rest is fine.
Right. Basically, those are the 2 points, but they're not all so fine. You see, there is this integral. The derivation doesn't assume that r is equal to r prime. It doesn't set r prime to equal to 0 because we are integrating over r prime. We are just summing over all possible values of r prime. But in the first integral, only the point r prime is equal to r contributes, and the result of the integral is the value of phi at the only point r. So it's only in the first term. If assuming, of course, r is in our volume. Now the problem is the second one, which is a problem, by the way. So G is divergent when r is equal to r prime. And we will see examples, and it does diverge when r is equal to r prime. So the problem is and it will diverge as 1 over their separation. It will always diverge. Now the problem is there are a few things that you can do. Either rho should be 0 at that point if you want to get a finite result. But if rho is not 0 at that point, well, it diverges, but there's no problem. You are sitting on a charge. And on the charge, the potential is infinite. So it should be infinite. So that's also fine. It diverges, but that's also fine. Now, the problem, it can be that, okay, you see, close to R, now this will contain a region, let's say a very small spherical region, close to the point R. Okay, so I have this charge density, let's say this is my position R. I assume a smaller sphere around it. This is the place where I have the divergence, right? This is the place, I mean, everywhere else that integral is regular plus regular part. Regular in the sense that there doesn't seem to be any reason for it to diverge. Only very close to this region, the integral might diverge. Now, very close to that region, the Green's function, this part, the Green's function is nothing but 1 over r minus r prime. Okay? Or let's just shift our origin to r. So the integral behaves like rho of r prime over r prime d cubed r prime. Well, if you look at this integral, we have shifted origin to r. If you look at this integral is, let's say, 4 pi, well, angular part. It just behaves like rho of r squared divided by rho of r prime, dr prime, plus the angular parts, which I separate the angular part.
How do you behave? How it behaves like that?
I'm using spherical coordinates. D cubed r prime is r prime squared dr. The numerator is r prime. Well, the rho can have some angular dependence, which I kind of write it as a factor. I mean, for my argument, it won't be relevant. Those are finite numbers. Angular integrations will turn out to be finite. So basically, my integral behaves like rho of r prime times r prime times r prime times dr prime. Okay? This integral is finite if, and also remember we are going to very close to r prime equal to 0. I can take this sphere very, very small as I want. Finite but very small. Rho of r prime at close to 0 will be finite if rho of r prime behaves like r prime to the power n, where n is larger than minus 2. Right? If n is minus 1, it's finite. As long as n is larger than minus 2, then everything is finite. There are no divergences in the integral. The integral is finite. Although it looks as if it is diverging, it does not. You see, before I was saying that the density should go to 0. The density need not go to 0. It can go to 0, but it need not go to 0. The density at that point can even diverge. But the divergence should be mild, in the sense that it shouldn't diverge faster than 1 over r squared. So as long as this is satisfied at the point r, where here this r prime is, you just take the r prime to be the distance from the point r. As long as this is satisfied, this integral, although the integrand itself seems to diverge, the integral is finite. So even if I have some charge density inside my volume, at the point where the charge density is non-zero, I can still have a finite potential.
So we are summing infinite stuff and
We are summing infinitely many, well, yes. On one hand, since the volume goes to 0, we have the 0 times infinity, but as long as this condition is satisfied, 0 times that product is finite. Furthermore, what do we know is that we know that rho of r prime, d cubed r prime, should be a finite number anyway. This already tells me that rho cannot really diverge very badly. If it diverges at anywhere, as r goes to r0, let's say, then rho should behave like 1 over r minus r0 to the power n, where n should be larger than minus 3. Otherwise, the integral will not be finite. There are still values for n between minus 3 and minus 2, in which the total charge will be finite, but the potential will diverge at certain points. We already know one example, the Dirac delta. If you have a point charge inside your volume, the total charge is finite, but at the position of your charge where rho is non-zero, where rho is divergent, the potential is divergent. But that's also fine. I mean, a point charge has a divergent potential at its position.
shouldn't be minus 2.
No, minus 3. Well, if n is between -3 and -2, the integrand is finite. When you separate, go to spherical coordinates, the radial integrand is finite. But the integrand can diverge, nevertheless the integral can be finite. That can be what we call the integrable singularities. They are divergent, but the integral is finite. Like 1 over square root of x. You can integrate 1 over square root of x starting from 0 up to some number. It will be finite, but at x is equal to 0, it diverges. One nice thing about this Green's theorem, by the way, is to create a potential, you don't even need a charge distribution in your volume. Well, if there are no charge distribution in your volume, the second integral, the volume integral, will be 0. Nevertheless, if the boundary conditions are non-trivial, you will get a potential from the surface integral, a contribution to the potential. Just like in the example, it was 8th or 9th example, where you have a sphere with the two hemispheres at different potentials. So you still get a non-zero potential everywhere else. Basically, you are putting some charges on the hemispheres to create that potential difference, which creates the potential everywhere else in your volume. Yes, other questions? Other questions? Well, let's do a bit in more detail this image charge for a grounded sphere. Sure. Which one? Point charge with two planes. How many degrees in between? 90. Where shall we put it? Somewhere over here. Plus Q. What are the images? Where are the images? This, let's say, is at a distance D. The charge.
Or let's say Q prime 1.
This, shall we say minus Q prime or Q1 or just Q, minus Q? So are you convinced that it will be just the minus Q, or shall we show that it has to be minus Q? Let's show it. Let's say this one Q1, this one Q2, and this 1 over 3 here, Q3. Okay. Now, we know the uniqueness theorem, which states that if we can find one solution that satisfies the Poisson equation and the boundary condition, then that is the solution. So that's what the uniqueness theorem is about. So my claim, my hypothesis is that the potential created by these 4 charges will be a potential that will satisfy the Poisson equation and it will satisfy the boundary conditions. So that is my claim. If I can show that, then I know that this is the solution. There are no other alternative solutions. So let's write the potential over here at the point R. Phi at the point R will be equal to, let's say, Q over R minus R cubed plus Q1 over R minus R Q1 plus Q2 over R minus R Q2 plus Q3 over R minus R Q3. This is my claim. This should be true for any. No, well, this should be the potential at any R, right? Now, first of all, does it satisfy the Poisson's equation in my domain? Well, let's see. If we act with the Laplacian on this one, this is minus 4q, 4 pi q, Dirac delta R minus R cubed, plus Dirac delta R minus RQ1 plus Dirac delta R minus RQ2 plus Dirac delta R minus RQ3. Remember, it should satisfy the Poisson equation in my volume. So R is somewhere over here. R can never be equal to RQ1, it can never be equal to RQ2, and it can never be equal to RQ3. So since R is never equal to RQ1, R is never equal to RQ2, and R is never equal to RQ3, basically in my volume, in V, Laplacian of phi is equal to minus 4 pi q times the Dirac delta R minus R cubed. Well, basically this is what I'm trying to solve. I have a single point charge in my volume, so this is the charge density corresponding to that single charge. And so the phi, this trial phi, satisfies my equation, my Laplacian equation, no matter what the values Q1, Q2, Q3, and the positions and their positions are, as long as they are out of my domain. So at this part of the proof is done. Now the next part, I have to show that this satisfies all the boundary conditions. Now the boundary conditions, since these are grounded, is basically phi at R when R is an element of my boundary. This should be equal to 0. This is my boundary condition. So this should be satisfied. Now let us take R1 to be this point, and R2 to be this point, and let's write the phi at R1. Now phi at R1 was equal to, well, you see, if I look at this R1 point, R minus RQ is equal to R minus RQ2. So this distance is equal to this distance because of the choice of the position of my image charge. And at the same time, this distance will be equal to this distance. So R1 minus RQ, the distance, is equal to R1 minus RQ2, and R1 minus RQ3 is equal to R1 minus RQ1. Okay, no matter where my R1 is. Now, if that is the case, you see R minus RQ is equal to R minus RQ2, and R minus RQ1 is equal to R minus RQ3. So I can write my phi as Q plus Q2 divided by R1 minus RQ plus Q1 plus Q3 divided by R1 minus RQ3. And this should be equal to 0. Well, I can go ahead and prove that Q plus Q2 and Q1 plus Q3 should be equal to 0, exactly equal to 0. But for the time being, let me just assume that this is 0 and this is 0. If I want phi of R1 to be equal to 0 for all possible values of R1, then those Q plus Q1 and Q1 plus Q3, they should both be separately 0. Otherwise, I cannot get phi equal to 0. Do you buy it?
There can be some other combinations.
Well, let's stick with this one for the time being. Okay, so this, if Q1 and Q1, Q3, they are 0, then this is automatically satisfied. There might be some other combination. We will see if there are.
So we did this because later we're going to test the other place, right?
Yes, now this is the condition that I obtained from the vertical side. Now let's look at the other side. Now if we are over here, let me not draw it, but the distance of R2 from this plus Q charge is equal to R2 minus RQ1. So the distance from this plus Q is the same as the distance from the Q1. And at the same time, R2 minus RQ2 is equal to R2 minus RQ3. So let's see, for R2, Q and Q1 are at the same point. Phi at R2 is equal to Q plus Q1 divided by R2 minus RQ plus Q2 plus Q3 divided by R2 minus RQ3. This should also be equal to 0. And let's say Q plus Q1 is equal to 0, Q2 plus Q3 is equal to 0. Well, let's see. The first equation tells me that Q1 is equal to minus Q. Did I make a mistake over here? Q1 plus, no, here I made a mistake. Let's see which two are at the same distances. Q and Q1, Q2 for R2, Q and Q1, Q2 and Q3 for R1, Q and Q2. Q plus Q2, this is Q2, sorry. I wrote it wrong. So Q2 is equal to minus 1. This tells me that Q1 is equal to minus Q, this equation. And Q1 is equal to minus Q, so this tells me that Q3 is equal to Q. And this also tells me that Q3 is equal to Q. So these are my charges. So let's go back. This was my configuration. So we found that Q2 is equal to minus Q, Q3 is equal to Q, and Q1 is equal to minus Q. So the primary images are of opposite charge. The secondary image, meaning that it's the image of an image, it again gets the opposite of the image, which is the same charge. Now back to your question, can there be some other possible combination of Q1, Q2, and Q3 such that the boundary conditions will be satisfied? The answer is no, because the uniqueness theorem tells me that there is a unique solution.
If we impose some strict conditions from the beginning, we may not reach a solution.
Well, you see, for example, we said that we have two kinds of boundary conditions. Dirichlet boundary condition and the von Neumann boundary condition. Now, we are always talking about one or the other one. We are never talking about both of them. We are never talking about, for example, saying that the value of the potential should be such and such and the normal derivative should be such and such, although we are talking about second order derivatives. We are saying specify only either the function itself or its derivative at the boundary. Because if you would specify both of them, then there are no solutions in general. Because if you specify the value, it already fixes what the derivative should be. If you just tell me that the derivative should be something else, there's no solution. But if you specify only one of the boundary condition, von Neumann or Dirichlet boundary condition, then the uniqueness theorem proves that there is a single possible solution. There is one, and it is single, unique.
So even if you don't fix the distance function, we make it a value, and the number will show as a real value.
Well, you see, of course you can make many modifications, like you can change the arbitrary number of charges, arbitrary distances, then the problem will be hard to solve. But we know that this is the only one. There are no alternative solutions with, let's say, 5 image charges.
Because we got one solution.
We got one solution. It is the unique solution. So there's no point in looking for alternative solutions. So that is kind of the power of the uniqueness theorem. If there is one solution, it is this solution. Of course, you can just work out some kind of a charge configuration, some alternative charge configuration, let's say, which behaves like a point charge. For example, instead of saying that, okay, I have a minus Q charge over here, I can just erase it and say that, okay, I have a sphere over here with a uniform surface charge density and the total charge is minus Q. Well, of course, this is an alternative solution, but in my volume, the two image configurations give me exactly the same solution. So there's no point in complicating the problem. Because what I did was I just replaced a point negative Q charge by a similar charge configuration which behaves like a point Q charge out of it, and I'm out of this charge configuration. Now we have the solution. So V, the phi at the point R, is equal to Q 1 over R minus R cube plus 1 over, let's say this is our delta, the position of this one is delta 1. Delta 2, delta 3, and this one is delta. R minus delta, 1 over R, well, delta 3 is minus delta anyway. R plus delta, minus 1 over R minus delta 1, plus 1 over R plus delta 1. This is my function phi. Well, this is actually my Green's function Q delta is equal to 1 over R minus delta plus 1 over R plus delta minus 1 over R minus delta 1 minus 1 over R plus delta 1. We have determined our Green's function. So let's do another example. While these two plates are insulated, they are insulated from each other. This one is at a potential V1, this one is at a potential V2. Now what is the potential? Or let's say this one is potential V, this one is at a potential minus V. Well, we already know the Green's function, so we can straight away write down the answer. By the way, if you look at from here, if you just change R and delta, the Green's function is symmetrical. Right? It's kind of trivial to see for the first two ones. It's a bit more complicated to see in the last two terms, but I mean, you can work it out. Phi of R, Green's theorem, tells us that this is equal to d cubed R over R volume, rho of R prime, g of R prime R, minus 1 over 4 pi ds, phi dg by dn, minus g d phi by dn. But on the surface, we know that g is equal to 0, our Green's function, so this term just drops. There's no contribution from that one. Rho is equal to 0 in our case. In our volume, there are no charge densities. This just drops down. So the potential at the point R is nothing but minus 1 over 4 pi integral of ds times phi dg by dn. Well, the surface these two planes. But phi, we can even simplify it a bit further. We can say that this is minus 1 over 4 pi times v, the integral over the vertical plane of dg by, what is the normal direction in this case? Let's say x, y, and z. For the vertical plane, what is the derivative with respect to n? Minus y, because it's pointing outside. And my plus 1 over 4 pi times v ds, the lower plane, horizontal plane, of, for the horizontal plane, what is the n direction? Minus z. So that's it. We know the potential. Well, if we can evaluate these integrals analytically, great. If we cannot, just tell the computer to do it numerically. And we know the potential everywhere without solving any differential equations.
We are not
Well, you see, that's a single point of dimension 0. So it doesn't contribute to our integral. I mean, you can set the value at that of the potential at that point to 0, for example. Or you can set it to v, or you can set it to minus v, as you like. As long as it's finite, it will not change the value of the integral. And you don't even need to set the potential to constant values on those two places. You can just imagine as complicated a boundary condition as you like. The only thing that will change will be it will be more difficult to evaluate the surface integrals.
So, why did we take G from the previous example to this
What is G in general?
is the G function that determines the potential and the boundary condition?
Yes, G is the solution, in fact, G is the electrostatic potential created by a unit charge with 0 boundary conditions. So here, if you want to solve this system, rather than solving this system directly, just first solve the problem of put a point charge somewhere, a unit charge, and set the boundary condition to 0, and solve that one. But that is what we did over here. We put some point charge over here, set the boundary conditions to 0, and obtain the potential. If instead of Q we put a unit charge, then Q should be 1. What we obtain is the Green's function, which you can use for this problem. So that's why I took the previous solution and put it over here. So that's kind of the nice thing about the Green's theorem. You don't need to worry about complicated boundary conditions. Just take the 0 boundary condition and put a point charge. If you solve it, then you know you can write down as an integral the solution of an arbitrary boundary condition. So let's go over the sphere example also. We have some, again, I can be interested in a problem in which the sphere has a complicated potential. And I can just look for the potential of that. I can connect it to various batteries, create some complicated boundary condition on the sphere, and then ask the potential everywhere outside the sphere. That's a decent problem. But to solve that problem, what I can do is just pick up the problem of a grounded sphere, grounded conducting sphere, and put a charge Q over here. And then what will be the potential at, let's say, some arbitrary point? Let's call this angle gamma. Well, Q is fixed, the position is fixed, the position, I'm looking at an arbitrary point R, not a special point, so I cannot really set gamma to 0. But for an arbitrary gamma, I can write the potential at the point R. Now again, I don't know the potential for the time being, at the moment, but I will just guess a solution. Okay, if I have this sphere, let us imagine some Q prime along that line, along the exactly same line, Q prime, at a distance d prime, whereas this charge Q is at a distance d. This is a guess. If I can show that the potential I obtain satisfies the Poisson equation in my domain, the same Poisson equation, and it satisfies the boundary condition, then I know that my guess is true and it is the solution. There's no other one. Well, if this is the case, then the potential at R is nothing but Q over R minus the position of Q plus Q prime over R minus R Q prime. Well, it automatically satisfies my Poisson equation. In our volume, Laplacian of phi is nothing but minus 4 pi Dirac delta 3-dimensional R minus R cube. Well, the other term, it also gives a Dirac delta, but its argument is 0 only outside my volume. So in my volume, the other Dirac delta is always 0. Okay, it satisfies the Poisson equation. The only thing remains is that does it satisfy the boundary condition?
What is the volume? Where is the volume that is equalizing?
Out of my sphere. So I'm interested in outside the sphere. You can convert it. I mean, you can also look at it inside the sphere, put some charge over there. But for
Same green function?
yeah, the Green's function will be more or less, yes, it will be more or less the same. So let's write it explicitly. Let's see, this RQ, let's write this as, it's at a distance d in the n direction, let's say. N is not the normal direction, but the unit vector in the direction of q. And RQ prime is equal to d prime in the n direction. So R minus RQ will be equal to square root of R squared plus D squared minus 2RD cosine gamma. And R minus RQ prime will be square root of R squared plus D prime squared minus 2RD prime cosine gamma. And this, let's see, R hat dot n hat is what I call the cosine gamma. So phi at the point R is Q over square root of R squared plus D squared minus 2RD cosine gamma plus Q prime over R squared plus D prime squared minus 2RD prime cosine gamma. And on the boundary, I have R, small r is equal to capital R on the surface of the sphere. So phi of R is equal to, on the boundary, Q over square root of R squared plus D squared minus 2RD cosine gamma minus plus Q prime over square root of r squared plus d prime squared minus 2r d prime cosine gamma. And this should be equal to 0 for all values of gamma. Well, there is one trivial solution. Well, you see, if you want to have these two things equal, the factors and the square root, they have to be proportional to each other at least for all values of gamma. One trivial solution is d is equal to d prime and q prime is equal to minus q. Then phi of r on the boundary, this is equal to 0, but we started by assuming that d prime is less than r. So d prime and r is less than d. This is our assumption. So d prime and d, they cannot be equal to each other. So this is not viable. Well, this solution basically gives me phi is equal to 0 everywhere, so it doesn't satisfy my Poisson equation. The other alternative is r, let's say r is proportional to d prime and d is proportional to r. This is an alternative solution. So let's see if this is possible. Now, so to show this, let's write phi at the point r as q over. In the first one, let's take the r out. One plus d over r squared minus d over r cosine gamma plus q prime over. In the second one, let's take the d prime out. D prime 1 plus r squared r over d prime squared minus 2r, so this is capital R, minus 2r over d prime cosine gamma. Now, if d over r is equal to r over d prime and q over r is equal to q prime over d prime, we are done. Minus. Well, let's see. This tells me that d prime is equal to r squared over d, which is, by the way, this is equal to r times r over d. R over d is less than 1, so this is less than 1. So we had determined what d prime is. And q prime is d prime over r times q. Well, d prime over r is r over d times q minus. So under this condition, the potential on the boundary is always everywhere 0. So we know our solution. Just put them over here, over this expression, and we know what d prime is, we know what q prime is, we know our solution, but this solution divided by q, it is our Green's function. So we can solve for the boundary condition for whatever charge distribution you have with whatever boundary condition you have on this sphere using this Green's function. And we are kind of done. You see, the thing that we are using over here is the uniqueness theorem. We are basically guessing one solution. It's called method of images because the additional charges that we find I mean, they more or less corresponds to an image if you would just look at a mirror of that shape. So that's one of the reasons why we call it the method of images. So by using the images and the charges of the images, we are guessing one solution, and then we are showing that that solution satisfies our Poisson's equation and the boundary condition, so it has to be the only solution. It won't be always possible, but it can simplify your life greatly when it is possible. And there are not many cases where it is possible. For example, in this problem of two conducting plates, unless the angle between the plates have some special value, you cannot really do method of images. You will get infinitely many images. So it won't be useful.
What do you mean special value?
Well, let's see. For 90 degrees, we said that, okay, we have this charge over there. There is an image over here. It also has an image over here. But this image, the lower image, has an image due to this vertical plane, which is over here. And this image over here has another image due to this horizontal plane, which overlaps with this one. So we don't need to go even further, because I mean, you can think that there is an infinite sequence of images, but this infinite sequence of images, they all overlap. Since they overlap, I mean, you just take the charges of the images to be the total charge of this overlap, and we determine those total charges if it is 90 degrees. Well, the same thing happens if it is 60 degrees. Let's say if it is 60 degrees, if you put a charge over here, it will have an image over here, and it will also have an image over here. Now, this charge will have an image due to this one, which will be over here. This will have an image somewhere over here. This will have an image over here, and that has an image over here. Again, everything overlaps. But if you just change this from 60 to 59, let's say, they start not to overlap. So if they are not overlap, you basically have infinitely many image charges at infinitely many different positions.
Basically, have a set.
I mean, the angle between them, you should be able to divide 360 to that angle, and you should obtain an integer. Well, if it is a rational number, that's also good enough. If it's a rational number, well, before you get the overlapping images, you will be going turns around and around many times. But then, even in that case, you will have many images, so it ceases to be practical. So in that case, we will use other methods to solve this problem, rather than the method of images. Questions? Okay, so on Friday you can just bring questions about anything that we had covered until this point, not necessarily only about the method of images, but bring questions. We will see. I hope I will not need it.